Hi, today I'm going to be talking about subnetting for humans. So it's a bit of a funny title, but subnetting is one of the more difficult concepts to really wrap your head around when you're getting into network engineering. And the reason for that is because the entire process is designed for computers and not humans, which means it uses the computer number system or binary instead of the human number system, which we normally use, which is decimal numbers. So the goal of this video is to show you that if you can start thinking in terms of binary numbers, the processes behind subnetting becomes a lot more intuitive and a lot easier to follow. Now that being said, a prerequisite for this video will be to kind of understand how binary numbers operate. So if you don't know how to convert a decimal number to a binary number or vice versa, then you should go and learn how to do that first before watching this video. So let's start with an overview of IP addresses. So IP addresses are 32 bits long, or 4 bytes, right? 8 bits in a byte. And they're divided into 4 octets of 8 bits each. And they're all separated by a dot. As we can see here, there's 1, 2, 3, 4 octets here. And they're separated by dots. And so this is the dotted decimal notation. And in the binary notation, we have the same thing. 1, 2, 3, 4 octets, and then 3 dots to separate them. Now, these two addresses are actually the same address. It's just one is in dotted decimal notation and the other one is in binary. And what you'll find is that if you convert this octet to dotted decimal, you'll get 192. So this octet matches up directly with this octet right here. And that's all the dotted decimal to binary conversion is, converting each of these octets individually into decimal or back to binary. When computers look at IP addresses, they'll see the binary form. And the reason dotted decimal exists is basically to help humans, understand the IP addresses better. If I were to ask you to memorize one of these, you'd probably choose to memorize the dotted decimal form just because it's so much more closer to what we're used to using. So next, we have subnet masks. So subnet mask over an IP address tells us which bits of the IP address are going to be network bits and which bits are going to be host bits. Basically, which part of the IP addresses differentiates networks from each other and which part differentiates hosts within those networks from each other. So there's also 2 forms of notation here. And the first one is going to be dotted decimal, which looks like a second IP address after the first IP address. So this would be your subnet mask here, and this is your original IP address. And there's also slash notation, which is right here. So again, and you can see the same IP address in the front. So again, these 2 IP addresses with subnet masks are actually the exact same. And I'm going to show you why that is in the next slide. So here we have those same IP address and subnet masks together. And I've actually gone ahead and converted this one into binary notation. So that I've converted the dotted decimal notation into binary. This section right here refers to this binary sequence, and this right here refers to this. So just from converting it to binary, we can already see like a pattern's emerged, which is you have a list of all ones and then followed by all zeros, right? So all the subnet mask is telling us is that anytime there's a 1 here, the corresponding bit in the IP address is a network bit. So these are all network bits from these first 2 octets. And whenever there's a 0, these bits are all host bits. So these 2 octets are all host bits. And as you can see, if you were to count up the number of 1s here, there's actually 2 groups of 8, which is 16, which is exactly how we get this number here, /16. I notice this is referring to the group of 1s. If I were to change all of these to 1s over here, if I were to change all these to 1s over here, we'd end up with a subnet mask of /24 because we're counting the 1s, not the zeros. So it would not be /8. A /8 would be if I changed all of these to 0. And we can do that because all subnet masks carry this format. It's a string of all 1s. It stops at a certain point. It can stop at any point here, but then after the 1's end, it's all zeros from there on to the end. So that's why we can just denote this subnet mask with the number of ones we have here. And it always starts with 1. There are 5 major main classes of IP addresses that we use today. A, B, C, D, and E. But for today, we're going to be ignoring class D and class E addresses. Our main classes we're going to be focusing on are A, B, and C. So class A addresses have a subnet mask of /8 or 255.0.0.0. Class B have a subnet mask of /16 or 255.255.0.0. And finally, class C addresses have a subnet mask of /24 or 255.255.255.0. So why subnet? The current IPv4 address space contains about 4.3 billion address spaces, which is a lot, but it's actually not enough for all the devices we have today. We've actually already run out of IPv4 addresses. So while we do have techniques like NAT, network address translation, to help with that, before we have to rely on those, we want to make sure we're using all our addresses as efficiently as possible. And if we go back to our classes of networks, class C networks, our smallest kind, each of them has 256 total addresses, or 254 hosts, which means that if you don't have 254 hosts in a network, you're going to be wasting addresses. Now, that's a lot of hosts, right? Most houses won't have that many. If you're trying to connect just a router to a router, you're going to only have like 2 hosts, so you're going to be wasting like more than 200 addresses if you're using a class C network for that. So the idea of subnetting is that we want to divide these addresses into these networks into smaller networks to more efficiently use up all these addresses. So as I just said, the idea of subnetting is to divide a larger network into smaller pieces, and each of these pieces is called a subnet. So what this means is that we'll have subnet masks that are not clean groups of 255 like we had in the past. For example, a subnet mask of /27 is 255.255.254. Now, this can be a little confusing until we convert it to binary and then realize that, oh, all that means is that there's 27 ones at the beginning of this subnet mask. Another way you can do it is see that there's 5 zeros here, and to go for 32, which is the total size of the IP address, minus the 5 zeros, and that'll give us 27. So a different way to get to the same answer. Now, there's 2 properties of subnets that we need to consider. The first is the number of subnets. So this is the number of subnets you're creating as you divide the larger network into smaller pieces. So the way we find this is using the equation 2 to the n, where n is the number of new network bits. And what do I mean by new network bits? Well, let's take a look at this example on the bottom here. We have a class C network, which means we have an original subnet mask of /24. That means that our original subnet mask would have ended here, right? I'll draw a line there. But now we're applying the subnet mask of /27, which means at the end, we turn 3 of these zeros into 1. So 24 plus 3 is 27, right? These new bits are going to be the new network bits, right? Because they weren't part of the original network. So that's what I mean by new network bits. So here we can see there's the number of new network bits. So our equation here is just going to be 2 to the 3, and that's going to be 8 total subnets. So if we have a class C network and we divide it into subnets with mask /27, we're going to have 8 total subnets. Now, the number of hosts. It's going to be very similar, except instead of network bits, new network bits, we're going to be using the number of host bits, or basically the number of zeros here. And we're also going to add this -2. And the reason for that is that we need to subtract the network and broadcast addresses, right? Remember, this is the number of hosts. The number of addresses in the subnet would be 2 to the m, right? But because we already have 2 addresses reserved, one is for the network address and the other is for the broadcast address. So we need to subtract 2 from this number to get to this equation right here. So for here, we have 5 zeros. That means 5 host bits, right? So we have 2 to the 5, and then minus 2. And that's going to give us 32. This is 32 minus 2, which is going to give us a total of 30 usable hosts for each subnet. So if we have a class C network with mask of 27, slash 27, we're gonna be able to divide that class C network into 8 subnets, each with 30 usable hosts. Okay, so let's get into some practice problems now. We want to divide the class C network 192.168.0.1/24, right? Class C network is always /24, into a subnet with at least 10 usable hosts. So part A of our problem is going to be, what subnet mask should we use? Now, what was the equation for the amount of usable hosts per subnet? It was 2 to the m, where m is the number of host bits, minus 2. In this case, we can make a bit of a table here, where we have m on the left side, and then the number of hosts, and then 2 to the m minus 2 on this side. Now we can go up. So here we know we need at least 10 usable hosts. If m is 1, this is going to be 0. And the reason why it's 0 is because there's going to be only 2 addresses in this space, but there's already 2 addresses reserved, right? If it's 2, it's going to be 2 to the 2 squared, 4 minus 2. That's going to be 2. If it's 3, it's going to be 2 to the 8 minus 2, or 6. Still not enough. If it's 4, 2 to the 4, it's going to be 16 minus 2, or 14. So now we finally have enough hosts if we have 4 host bits. As you noticed, this is not an exact match, right? We're going to have 4 more hosts than we actually need. But subnetting is not exactly perfect. Sometimes we're still going to have a few overflow. But this is certainly much better than using the whole class C network and having the 254 hosts for a network where you only need 10 hosts, right? Our answer for this is going to be that we need 4 host bits. So if we have 4 host bits, that means 32 minus 4 is going to be 28. So our subnet mask for this is going to be /28. Or in binary, it's going to be, I believe, 255.255.255.240, I believe. Yeah. So 3 255s followed by a 240 at the end. That would be the dotted decimal notation to write this subnet mask. So for part B, it asks us, how many subnets of this size can we make? Remember from the previous part that our subnet mask is going to be /28. To calculate the number of subnets we can make, we need the number of new network bits and raise 2 to the power of n, right? So it's 2 to the n, where n is the number of new network bits. Our original class C network had 24 network bits, and now our new subnet has 28. So that's 4 new network bits. So we have 2 to the 4 subnets, which is going to be 16. So in total, we're going to have 16 subnets. And remember, because this is the number of subnets, we don't have to do the minus 2. You only have to do that for the number of hosts. So part C wants us to find the usable address range of the first subnet. So we're going to have to take a look at this IP address now. Now, the original class C network was a /24, which meant there was a divider here. Network bits here on this side, and host bits only are here for this one octet. And for this class C network, these 3 octets were going to remain constant. They would not change. And that means for the subnets that we created out of dividing this class C network, these octets will also not change. So the only thing we really have to worry about is this last octet. So 1, 2, 3, 4, 5, 6, 7, 8 spaces. An octet, right? And remember, because we have a /28 subnet mask, that means that we have 4 new network bits and 4 host bits. So we divide this cleanly down the middle, 4 host bits here and 4 new network bits here. Now, we know that we're only talking about the first subnet, which means that we know that these host bits, sorry, these not host bits, these network bits, these subnet identifier network bits are going to be all 0 because that's the first subnet. Remember, these can go from range of 0000 all the way to 1111. And that's between that's going to give you your 16 different subnets that we calculated in part B. Now, the first usable address here is going to be 0001. And it's not going to be all zeros because that's already reserved. Remember, that's already reserved for the network address. And same thing, the last usable address in this range is not going to be all ones. It's going to be 1110 because the broadcast address has already reserved the space, the address of all ones in the host bit. So if we convert these binary, this entire thing in binary over to dotted decimal, we'll get 0.1 here and 0.14 over here. So our range of usable addresses for the first subnet is going to be 192.168.0.1 here, all the way to 192.168.0.14. And that's going to be our usable address range. So part D, our final part, wants us to find the network address and broadcast address of the second and third subnet. So there's two ways we could go about this. The first one would just be to write out the addresses, right? We know there's 4 host bits and 4 network bits in this final octet here, right? And we know that if the first if the network bits for the first subnet is going to be 0000, the second subnet is going to be 0001. And then we know that the network address and the broadcast address are all going to be all zeros and all ones. And we can convert this to binary, which will give us .16, and then this one is going to be .31. That is one way to do it. However, what if we wanted to do a little faster? If I write out the network address of the third subnet, it's going to be 0010, right? This is 3 in binary. And then go to 0000, we're going to get .32. And do you notice a pattern between the network addresses here? It went from .0 for the first subnet to .16 for the second subnet, and then to .32 for the third. And the reason this is because we have 16 total addresses in each subnet. So 2 to the m, but without the -2 for the hosts, because we're talking about addresses. So it turns out that if we have a subnet and we know its network address, we can find the next subnet's network address just by adding 2 to the m. In this case, it would be 16. So let me go. Subnet 2, network, broadcast. Then subnet 3, network, broadcast. So here we've already written a few out. So .16, we can find that we've already written out this network address of the second subnet. We know it's .16, but we could also just have added 16 to the network address of the last subnet, which we knew was 0, right? And same thing for this one, .32. And the broadcast address is always just going to be 1 less than the network address of the next subnet. So this is going to be .31 here, and this one, well, in order to find this, we can just go to the fourth subnet, right? Add 16 again to get 48. So we now know that the network address for the fourth subnet is .48, and then subtract 1 for that for .47 for the broadcast address of the third subnet. So that's a quicker way to do it than writing them all out and converting it back to binary. But both of them will get you the correct answers. And I should also mention that all of these are only referring to the last octet. All of these addresses need to be appended onto 192.168.0 and then you can have .16, .31, etc. So that's all. That's an overview of subnetting, and we walked through a practice problem with a lot of parts, and those will cover basically most of the different types of questions you'll be asked on the subject. So I hope this video is able to help you, and I'll see you next time.